to deal with silane, number C. I'll start again. I'll do it in green. I start with the silicon, the unique atom. I place it at the center. I draw the hydrogen atoms, distribute those about that central position, and I'm going to erase this number F here for now. We'll deal with it later. So I have room to work. I have silane, which is group number 4, silicon, which is group number 4. So I have 4 electrons for that, plus I have 4 hydrogen, which is group number 1, which equals 8 electrons again. So now I will distribute these 8 electrons. First I'll draw a line connecting the central atom to the outer atoms, and I'll deduct 2 electrons for each. That's 2, 4, 6, 8, so minus 8 electrons. I have 0, so I'm done distributing electrons. And now I just have to check to see if the Lewis demands are satisfied. And the demands of the hydrogen atoms, the outer atoms, are all met because they require 2 electrons to give it the closed shell configuration. And the central atom requires 8 electrons to complete to give it the closed shell electron count of 8, and I have 2, 4, 6, 8. So we've satisfied Lewis. Now all we need to do is, erase my scratch paper. Now I need to determine what type of E-pair geometry and molecular geometry is going to result from this type of a structure. Well, I've got 1, 2, 3, 4 electron pairs associated with the central atom, and that is going to demand a tetrahedral E-pair geometry. And in this case, there are no lone pairs on the central atom. So that means that the E-pair geometry is going to be the same as the molecular geometry. It's going to be a tetrahedral molecule. And so now I can write my answer, draw it with the proper form, and we'll start with the hydrogen up here, come straight down, draw my silicon, come over at a 109.5 degree angle, and draw my hydrogen there. That's all in the board. And now I'll come out with my wedgie to denote the hydrogen that is 109.5 degree angle out in this direction, and my dashed line depicting the other hydrogen. And now I've completely drawn the silane molecule with the proper molecular geometry. And now I have to determine what the formal charge is. So I'll do my little table. The atom and the formal charge. Now I've got silicon. And here I've got 1, 2, 3, 4 electrons, and it's group 4. So 4 minus 4 is 0. I got another 0 formal charge, and I've got my hydrogens. And each one has 1 electron. It's group 1. 1 minus 1 is 0 again. So I've got the 0 formal charge all about, and we're done with this particular case. Now, number D, which is sulfur dioxide. I'm going to start out with my sulfur molecule in the middle. My oxygen's disposed about it. And now I'm going to add up the electrons. They're all group 6. So I have 3 times 6 equals 18 electrons. And now I'll draw a line connecting the central atom to the outer atoms, deduct 2 electrons for each such bonding pair, give me 14 electrons remaining. Now I have to distribute these electrons first to the outer atoms in order to complete its closed shell demand, and that means, as always, with everything but hydrogen, it's going to require 6 electrons for each of the outer atoms. So that's going to take care of minus 12 electrons, and there's going to be 2 electrons remaining, which, so I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I've got 2 electrons left over, which I will place on the central atom. So we're done distributing all the electrons. It's essential that you follow this sequence religiously because of what is about to occur. Now I have to check to see if the demands of the Lewis structure, which are that each atom have its closed shell electron count, is indeed satisfied. Well, it is satisfied for the outer atoms, but the central atom, the sulfur, has 2, 4, 6 electrons, and it's too short of the required 8. The reason we follow this sequence religiously is because we're going to have to evoke multiple bonding in order to complete the demands of, or satisfy the demands of the central atom. And you never use the lone pair that was assigned to the central atom for multiple bonding purposes. I can take a lone pair from one of the outer atoms and then place it as a bonding pair between that and the central atom and see if I've satisfied the demands. Well, taking one of such pair, I've already got the needed 2, 4, 6, 8 electrons with the central atom, and I've still got 2, 4, 6, 8 on the outer atom I used the lone pair from. And so now we satisfied all of the Lewis demands, but still it reveals that we're not quite done yet because I have inequivalent oxygen atoms. One oxygen is double bonded to a sulfur, and one of the oxygens is single bonded to the sulfur. And if this is one of the shortcomings of the Lewis approach, is this would suggest that I would, if I were to take the molecule of sulfur dioxide and measure the bond lengths, that I would have one short bond and one long bond, 2 inequivalent bonds. And what in fact is observed with sulfur dioxide is only one bond length, and it is shorter than a single bond but longer than a double bond. It's intermediate between the two. And so the way we depict this in a Lewis sense is I will have to draw brackets around it, and I will draw a double-headed arrow. This is resonance. And I will draw the same molecule, but this time the oxygen on the right is going to get the double bond, the oxygen on the left would be a single bond. So I'll draw that. And now I've completely satisfied the Lewis demands. Now what this represents does not mean that this double bond is shifting between the two. The way to interpret this is that it is the statistical average of the two. In other words, the bond is not a double bond and a single bond. It is actually 1.5 bonds. So, you know, if I have 3 bonds distributed in such a fashion, I would want to, if I could, draw 1.5 bonds between the oxygens and the sulfur, and there is no way to do that. So this is why we have to evoke resonance. That it's not interpreted as actually something that's physically going on. The physical entity we're trying to represent is the average of these two. So with that thought in mind, now I can address the molecular geometry and the E-pair geometry. So I can pick either one of the resonance forms. It doesn't have to be both. Just one of them, and then I can draw the molecules with the appropriate geometry. So I'll take this one as an example. I've got how many E pairs associated with the central atom. Well, here again, we're going to have to take into account that for geometric considerations, and that has to do with electron pair repulsion, this double bond is localized between the sulfur and the oxygen, so we treat a multiple bond, a double bond, a triple bond, and a single bond, all the same. Because geometrically speaking, they're localized in the region between the atoms, so it counts as one pair. So on the central atom I have 1, 2, 3 E pairs, which is going to demand trigonal planar E pair geometry. And I have a lone pair on the central atom. So the E pair geometry is not going to be the same as the molecular geometry. So I can draw the molecule now with the proper geometry, and then I'll draw the resonance form in the same fashion. But first I'm going to start with the central atom, the sulfur. I'll put the lone pair up here. So it occupies one of the trigonal planar sites. I'll draw this bonding pair coming down in the plane of the paper, the double bond. And so it is taking up one of the next trigonal planar site, and this bond, single bond coming down to this oxygen, which is taking up the other trigonal planar site with its lone pair electrons. And I end up with the molecular geometry that I would predict, where I have trigonal planar E pair geometry and one lone pair on the central atom. I'm going to end up with a bent molecular geometry. So I will now include the resonance forms. I'll put it in brackets, and this time I'll redraw it with this oxygen single bonded to the sulfur. Close the brackets. Now I can assign the formal charge, but I have to now be able to unambiguously discuss the single bonded oxygen and the double bonded oxygen, which are distinct from each other, and they're going to have different formal charges. So I got the atom, formal charge, and I have to have an unambiguous, so I'll start with the sulfur, which is the same in both cases. And the sulfur is going to be, I have 1, 2, 3, 4, 5 electrons associated with the sulfur. So I have to take the group number minus the number of electrons. Sulfur is group number 6. 6 minus 5 is plus 1. I have a plus 1 formal charge associated with the central sulfur atom. Now I have to make the distinction between the double bonded oxygen and the single bonded oxygen, and I'm going to do that this way by taking an O and drawing 2 bonds coming out. And now I will count the electrons associated with this oxygen. 1, 2, 3, 4, 5, 6. Oxygen's group number 6. 6 minus 6 is 0. So I have 0 formal charge localized on that particular oxygen. And I'm not suggesting that there's actually a charge. This is just a bookkeeping device, but it works. And now I'll deal with the oxygen that's got a single bond. I'll depict it that way. And I'll count the electrons. 1, 2, 3, 4, 5, 6, 7. So it's group number 6. 6 minus 7 is minus 1. And please note, as a check, the sum of the formal charges has to add up to the charge on the molecule, and indeed it does. Plus 1 plus 0 minus 1 is 0, and it's a neutral atom. A neutral molecule. So we have now completed the answer for that particular problem. And now we only have 2 more molecules to do.